Welcome to this Robotics 2 lecture on collision detection and robot reaction. This is the second of the topics about research that has been conducted in our lab over the last few years to be included in this series of teaching lecture. So, I will present, in fact, the problem of handling robot collision in a more large perspective, namely that of safety in physical human-robot interaction, which has the English acronym of pHRI. This topic has become of paramount importance in the last few years because of more increasing need of having robot working next to workers in an industrial setting and later on in a very short future, probably also in other environments at home and so on. Our work has been funded over the years by a number of European projects that we gratefully acknowledge. First, the FRIENDS project. FRIENDS is an acronym that stands for Physical Human-Robot Interaction and Dependability and Safety. Then we moved to SAPHARI. In fact, I had the privilege of leading this European project as a scientific coordinator. SAPHARI stands for Safe and Autonomous Physical Human-Aware Robot Interaction. You see that physical and interaction are coming in different ways in these acronyms. And last but not least, we worked in the project Simplexity, which was more industrial oriented, and we will see some results of this project in this and probably more in the last lecture on human-robot collaboration. So, what do we need in order to achieve safety in this human-robot interaction? We need what is called dependability. Dependability is something that goes beyond reliability of components, of software, and so on. Means that we have a human user should have the feeling of being dependable on these robots that are living next to them. And this requires a number of steps in order to be pursued. The first one is mechanics. We need to have lightweight robots. We need to have robots that may display compliance both at the hardware level and at the control level. Indeed, we will never realize, say, physical interaction with huge robots that weigh 1,500 kilograms or so. This makes no sense at all. There's another aspect which is important, namely that more and more, and I would say the next generation of robots will have not only compliant actuation, so joints that are connect motors and driven links through compliant transmission, but variable stiffness actuation devices. So the possibility of including an online scheme, so a second motor, if you wish, that allows to change the stiffness in real time to adapt to the various situations. Apart from that, so apart from these devices which are internal to the robot, we may need typically more and more exteroceptive sensing, because we have to monitor the environment, we have to understand what are the intentions of the human, and so on. In fact, motion planning is also very important, motion planning for the robot. So, in SAPHARI, the consortium developed a human-oriented motion planning scheme that generates legible trajectory of the robot so that the human can understand what the robot will do. For instance, in the handover task, so while the robot is giving something to the human. And indeed, also control strategy should embed safety objectives and also constraints in their design and should be not only and probably not mainly devoted to accuracy and repeatability, but really to understand some uncertainty or unpredictable situation and move the robot accordingly. So there are various phases in this interaction, and now we are interested, in fact, in collision. So collision, in fact, should never occur, so we should prevent by planning, by controlling, by monitoring that such events occur, and if we are getting closer, we should let the robot avoid as much as possible these collisions, so unintended contacts between the robot and the environment, in particular the human. This is our main goal, but in fact this is important also for other type of dynamic environment. But if this happens, and this may happen because we want to bring closer and closer the lightweight robot with the human, and the human may do very fast motion which are unexpected, and even if monitored, the robot is not able to avoid them. So eventually we should be able to detect and react to collision. And react means not only stopping, as we will see, but probably also escaping this dangerous situation. Now, I mentioned exteroceptive sensing. You can imagine that you may have cameras or laser sensing, proximity sensor that recognize the situation. But in fact, to detect and react to collision, the most robust way would be to use only proprioceptive sensor in the robot. So the sensor with which the robot is already equipped, because these are very reliable. They don't need external appendage or setting up setting up a sensory system around the robot. So we will pursue this avenue, to detect and react collision using only proprioceptive sensor. In fact, there are, in this context, we developed also a framework which we call collision event pipeline, where different phases can occur, and we will see what is important and what are the goals within the single phases. So the collision event pipeline, I'm referring to a paper that was published in 2017 after long preparation, I should say. So this work started 10 years before, maybe. So you can see that there's a number of issues. You can recognize also terminology that we have used also for fault detection and isolation of actuator faults in a previous lecture. In fact, as I anticipated, we see the collisions as a fault occurring in the system. But this is not the whole story. So you can recognize in this long chain a pre-collision phase. Pre-collision means the robot is coexisting with the human, is doing its task, and the human is doing his or her task as well. So we try to bring them together, close together, but in fact avoid any collision. And in order to do this, we should know the context in which the operation is being performed. But if this happens, if collision cannot be avoided, we have to detect. And detection as a fault may just a non-off event. So false or true is what we are looking for, and we need some monitoring signal in order to detect collision. The next step, at the same time, if you wish, is also isolation. Like we did FDI for actuators, we will do FDI for collision. And isolating a collision in a robot means essentially understand where this happened. So more specifically, which is the contact point at which collision occurred, and this is important also for later stages in this framework. But at least, if not so precise, at least which link has collided among the n link. of the robot. Because this collision may occur, and contact in general may occur at any level, not only at the end effector level. This may be more interesting for industrial application, where the end effector is the most dangerous part of the robot because it holds a tool, and this tool may be dangerous for the human. But in fact, we can cover all situations at the same time with our approach. After isolation, or also together in parallel with isolation, we would like to identify the type of collision, which means essentially to understand what are the history of contact forces, of external forces acting on the robot. And this may be done at the Cartesian level or also at the level of resulting joint torques coming from external signals. So tau and F stands for this quantity. Tau are generalized torques. I mean, we assume that the robot has revolute joint, but this is not necessary at all. So that could be joint torques or joint force, while the calligraphic F stands in general for forces and moments, or generalized forces in the Cartesian space. And once we have detected, isolated, and identified this collision, we may start classifying their nature. So if they are accidental, and so they should be treated really as collision, or if they are intentional contacts, which may be the understanding that the contact is intentional because we would like to kinesthetically or physically interact with the robot and start a phase of collaboration, which is something completely different, and that we will treat, in fact, in the next and last lecture of our Robotics 2 course. If it's accidental, so if it's a collision, if it's light or severe, and then like we discussed about general faults for dynamic system, this may be transient, incipient, repetitive, and so on and so on. Now, in all these phases, we have been using monitoring signal, but when we classify, of course, we need to know also the context. This is important. So the two lines that are going through this series, this pipeline of the collision event, as we organize this, at this stage, the classification needs to know what the robot is doing, what was the context in which this contact occurred. And similarly for the reaction. So the robot, once this has been done, and pay attention, these phases may be really simultaneous. Everything may happen in the time span of few milliseconds. Okay? So the reaction of the robot may just stop or slow down, or do a reflex control, and there are many other things that can be done at this level. And we will see a few of possible robot reaction, not just stopping the robot. Of course, you react more intelligently if you understood more about the collision. If you just detect a collision and it's an on-off, then probably the only reaction that you have available is to stop the robot. But if you understood where this collision happened and why it happens and what type of nature, your reaction may be much more sophisticated than that. And of course, once you react, you have a post-collision phase. For instance, you start a collaboration if you understood that there was a soft intentional contact, and this is a mean of saying by the user that he or she would like to start an interaction where contact should not be avoided but should be part of a physical collaboration task. Okay, with this in mind, what about the current state in industry? In fact, this slide may be a bit outdated because more and more industrial robots are coming with sensitivity features. So the fact that they are able to detect a contact and then react to them. They are compliant, as we have seen in our introductory lecture of Robotics 1. In fact, KUKA lightweight robot but also ABB, YuMi robots, and other new generation of lightweight robots, like the universal robot that we have also in our lab, they are capable of understanding that some extra contact has occurred. But in fact, most of the time, they are only focusing on detection of contacts and labeling them as collision in this context. How do they do? So I'm listing now a number of possibilities. These possibilities have been explored also at the research level. So I'm not saying that various companies are using one or the other of this method, but these are all the options that are available for doing this. I will come back later, in particular, to one of the methods that we developed, which was in fact implemented in KUKA industrial robots of the lightweight generation, IVA, and so on. Okay, so as I said, most of these methods allow only detection and not isolation. And what can you do? So first of all, you may imagine that you're controlling your robot with some scheme. So you're sending motor currents and you're measuring motor currents, or you have a command that you rely on it. In fact, if the actuator are not failing, the torque that you're commanding are those that are also going to the robot. So all of a sudden, you may see at some instant tk of your discretized time, because in fact you're using digital control, that your torques, or if you wish, your motor currents, are very different from the previous sampling instant. So they are larger than some epsilon, which may be constant or may become a function of the trajectory that you're doing, but this is for the time being irrelevant, because we will not pursue that. And of course this can be organized in a vector level for all the torques, or joint by joint, and at least one joint has this sudden jump. So this may be a suggestion, may suggest that a collision may have occurred, and this is one method for detecting collision. You may also be more sophisticated if you have the first method, of course, requires no model at all, no dynamic model at all of the robot. It's just based on the variation of the commands that you're sending. And of course, if you have collision and you're trying to do a task, the variation, for instance, if you're having a PD control, indeed you will see a larger error and then a larger torque, and this is why you suspect that a collision may have occurred. The more severe is the collision, larger will be the deviation. If you're following a trajectory and you're doing position control, so you're really relying very on accurate execution of a desired QD of time, you can have a model and you can compute, including possibly also friction in this context, so the last term in this expression. You may have computed in line or before starting a profile, a nominal profile of the expected torque, and this is in fact an inverse dynamic computation. And when you're really running your experiment, you're running your execution of the task, no matter if you're using this torque or not, but if the torque is very different from what you expect, because your controller is imposing the right trajectory, then this may be another indication that a collision may have occurred. More than that, you can not use just the desired trajectory, but use the current measurement of the state of the robot, so Q and Q dot. You don't have a measurement of the acceleration, so you may estimate numerically the acceleration. I'm calling the signals Q double dot n as numerical estimate, and if you plug into the model that you're using together with the measurement of the robot state, you may have an expected nominal torque, and if this is the torque that you're really measuring through the motor currents, for instance, is very different from this, then again, the cause may be a missing term which is coming from the colliding force acting then on the joints as a reflection. And finally, you may also not estimate the acceleration, but compute it from a simulation that you're running in parallel. You're sending the command that you're sending to the robot also to a simulator. You simulate your system, which means that you're computing the acceleration, namely you have to invert the inertia matrix of your robot, and with this acceleration you integrate once and twice to get the new state. So if this computed new state, QC and QC dot, is different from what you're measuring in terms of position and on velocity at some instant, and it's very large, this difference, or exceeds some threshold, the epsilon stands for threshold everywhere, then you suspect that something has happened, and in fact another indication of collision. You see that all these are variation of processing signal. The first method only is signal-based, all the others are model-based, but they use, in fact, the model and something more like inverting the inertia matrix in real time, or estimating in real time the acceleration and so on, or relying on your controller for executing accurately a position trajectory. So, but in all cases, first of all, only detection is maybe guaranteed or maybe expected, and not isolation. So you have no idea which joint, which link has undergo a collision at this stage. And all these methods are quite sensitive to which type of controller you're using, torque control or position control, what type of motion are you doing while in your regular operation of the task, of the robot, and this of course makes harder to define also threshold. At least for this reason you have a sensitivity to this type of situation. And in particular the last two methods, beyond the availability of a model, which we will need also in our method. In fact, identification of a good model is a basic step in all this process. So if you may require acceleration estimate, which are typically noisy, or the inversion of the robot inertia matrix, which is computationally expensive in a sense. Okay, so still something can be done. In fact, no matter which method ABB is using, here is an old video that shows a massive industrial robot with a heavy payload hitting an old car body and stopping its reaction. So this was intended, probably they used some current measurement information to understand that a collision occurred, so the trajectory of the robot was going through the car in principle. When the collision occurred, the robot was stopped. So this is something that can be done. Of course, we are now interested in much lighter robot in this case, but just to have an indication that something could have been done also before, many years ago, with this purely detection provided by the ABB software. Okay, so let's focus on our method and consider the model, the dynamic model of the robot in this form. And first thing to note is the inertia matrix, the Coriolis and centrifugal term have been factorized, and this is very important now. This should be a good factorization, namely one that guarantees the property that m dot minus 2s is q-symmetric, like we have seen, for instance, in adaptive control or in passivity-based trajectory tracking controller. We need this factorization in particular. On the right-hand side, we have the control torque, tau, so we are changing notation here, we call the control torque tau, and we have another tau which is the joint torque caused by a link collision, if present. Otherwise, this is zero. This formalism, apart from moving from u to tau, is very similar to what we have seen in case of actuator faults. The only difference is that we modeled that faults with the subtraction on the right-hand side. So we wrote at that time u minus uf, where uf represents a fault which subtract actual torque to the command. Maybe for this reason I prefer here to use a plus, because this is in fact an additional torque which will move even more, or try to move even more, if not contrasting in fact the robot because of this collision. So the tau total is the sum of the applied control torque, our intended command, plus the effect of a link collision. So tau top will be all the right hand side. Of course, this tau k, another comment, the k stands for collision, so collision in German, because this work, I performed this work originally, and I developed this work, the idea was already there, during my sabbatical at DLR. This is why the first video that you will see have been shot at DLR in Munich. So this tau k comes from some generalized force, so force or moments or combination, that occurs somewhere along the structure, at the end effector or in a different area of the robot structure. So this force is being transformed into a joint collision torque by the Jacobian transpose, but this is a Jacobian transpose which is associated to where the collision occurred. So in general, we don't know what is the force or moment being applied. We don't even know the position, so we don't know even the Jacobian of the contact point, so the jk. So the whole tau k is certainly not known in advance. Okay, so this is a very obvious observation. So we know tau, but we don't know tau k because of a number of reasons that I just mentioned. So collision may occur at any unknown location along the whole robotic structure. This gives much power to our method, and also allows us to ask ourselves if we are able not only to detect the collision but also to identify, to isolate the link at which this occurs, and we will see that one of the methods that I will discuss allows also to do this. There are some simplifying assumptions. Some of them may be relaxed. For instance, we assume that our robot manipulator has an open kinematic chain structure. You may modify the method for other situations. For instance, if you have a closed kinematic chain, like in humanoid, what I will call the momentum-based method, in fact, has been modified to cover also this situation. The principle remains the same. The second simplified assumption, which is not strictly needed, is that we have a single contact or collision at the time. We may also have multiple collisions at the same time. We can detect this, and also probably isolation would be more difficult in that case. Another simplifying assumption, as you can see in the model, there are no friction terms. You may assume that friction is negligible at this stage, or better, that has been identified, and if friction is present, has to be identified in fact and used in the model. So wherever you will find in the expression of our monitoring signal terms coming from the model, if friction is relevant, also friction should be included, unless I will specify that this is not needed later on. Okay, so these are our simplifying assumptions, and the method that we've developed are based on first principle, let's say physical principle. So we are not relying too much on a methodology that is related to a specific robot. but it's a general methodology. Before doing that, let's analyze what happens for a collision. So this is our old friends, the 2R planar arm, under gravity or not, it's not relevant at this stage. And here you can see a couple of possible forces, pure forces in this case, that collide. In general, you have kinematic of the colliding area. So you may define a Jacobian that relates the joint velocity to the area on a specific link where this colliding generalized force happened. So you may have the Jacobian, which is decomposing the linear and the angular part, and associated you have a generalized force, which lives in R6 in general, so linear component and momentum component. But for the time being, assume that this capital Fk is just the two-dimensional force acting on the first link in a specific position and on the second link. Now, if these forces are applied in a quasi-static way, so in a situation where we are holding the robot at rest through control and we apply these forces. Now, these forces, if a force is applied to a generic link I, in this case I is only equal 1 or 2, then this force, in order to keep static condition, should be balanced by torque that are applied only at joints that precedes the link at which this contact force has been applied. For instance, if we are considering the first case, the Fk on the right, the one coming downward on the first link, of course, in order to balance this force and keep the robot at rest, we need to apply only an additional torque at the joint 1, as related by the Jk1 in this case. On the other hand, if we are applying the force on the second link, represented by the second orange arrow, Fk, then in order to balance this force and keep the robot in equilibrium, then we will need a joint torque both at joint 1 and joint 2. So you see that if you continue with the story, in the generic case, if the static contact force from the environment is being applied on the robot being held in a certain position through control, then we will need to balance this external contact force only torques at preceding joints. And the assumption that we have a serial manipulator here matters. But this is not the case of a collision. Of course, we can have a collision also while the robot is at rest and not moving and controlled to stay in this position. So this is relevant also in this case, but more relevant is dynamic condition. So if we have a collision, for instance, on link 1, and while the robot is moving, then this will contribute to accelerating, in general, all the joints and therefore all the links. And same for the collision at the second joint. So you have, through the inertial couplings and through the effect of Coriolis and centrifugal terms, and also gravity matters here, when the robot is in motion, so when we really care about collision, then we will have a mix-up of situation. So this Fk, a generic Fk, will generate a tau k through the proper Jacobian only on that joints, but the acceleration, which will modify the motion of the robot, will be produced at all joints. Okay, so this is a very important observation, and we will try to counteract to this, making the dynamic situation very similar to a static one. In this way, later on, we will see that we are able also to isolate at which link the collision, the dynamic collision occurred. Okay, with this in mind, let's recall some relevant dynamic properties that we have already seen while doing dynamic modeling. The first one is related to the total energy of the system, so the sum of the kinetic energy and of the potential energy. We are now assuming that the robot is fully rigid. The model that we have seen, in fact, is a model, dynamic model of a rigid robot. We have seen that there's a property, very important, that says that the variation of the total energy of the system is equal to the work done by the applied external forces. Now, in this case, there's not only tau, so E dot is equal to the scalar product of the velocities times the total applied external or non-conservative, but in fact torque. In fact, if we assume that we have a negligible friction, all these torques are only contributing to motion, and the tau tot in our case will be the torque produced by the motors, but also the possibly joint torque resulting from an external collision. And this is a first equation that we have to keep in mind. The second is a vector, in fact, information, still from basic principle, namely related to the generalized momentum of the robot, so the product of the inertia matrix times the joint velocity, so what we call P. And in fact, we know that we have a dynamics in terms of P, and this is an explicit form for the dynamic of the generalized momentum. And you see that apart from some terms which are coming from the model, if friction was there, also friction would be present on the right-hand side. Pay attention, there are different signs, there's a minus G, and moreover the Coriolis and centrifugal term are not as such, but we have the transpose of the matrix S, which factorize, suitably factorize the Coriolis and centrifugal term. And the most important thing is that we have a decoupled relation between each component of the generalized momentum and each component of the total torque, joint torque being applied, coming both from the motors, but also from a possible collision, as we have seen before. So just a side note here, for those who are following the full course, this is in fact the same, is the vector version of the same formula that we encountered for actuator FDI, or in particular when we dealt with dynamic modeling, and we could write down state equation, and I mentioned that in place of Q dot you may use a state component, also the generalized momentum, and that would have been the resulting equation, first order equation for the generalized momentum. Okay, now one important aspect, in order to get to this expression, we need the skew symmetric property. So we need to use the fact that the factorization S times Q dot, to which we are representing Coriolis and centrifugal term, is one that guarantees M dot minus 2S being skew symmetric. But apart from that, this, as a consequence, is that M dot in fact can be replaced by the sum of the S matrix and the S transpose matrix. And in fact, this is why you see the S transpose matrix appearing on the right hand side of this expression. And I would leave you as an exercise to prove that this expression is correct once you start with a model that has a factorization with S that satisfies M dot minus 2S being skew symmetric property. The proof is quite elementary, but it's interesting to work it out. Okay, so these are the relevant dynamic properties that we will use in the following. And before writing down the monitoring signals that allows us to do first detection and then also isolation, let's look at the general block diagram which describe what we are doing now. So the robot is under normal mode of operation, is doing something, so we are sending torque commands to the joints, and the robot is moving. Now, at some point, some external forces, generalized forces, will be applied, so we will have a collision. And we like to detect and to isolate those collisions without using external sensors, so cameras, or even surface tactile sensory through which we can equip the robot. Pay attention that this solution is being pursued, at least in research laboratories. So to put a sensitive scheme everywhere so that we can detect forces by direct sensing, without using sophisticated model, but in fact the sensor is quite sophisticated and quite delicate, I would say, at this stage. So for doing this, we send to a different, let's say, dynamic system, in fact a software unit, the state of the robot, so Q and Q dot, and also the torque that we are applying. And we call this dynamic system, it's a residual generator, I would call it. In fact, here we call it collision monitor, that generates some signals, and these signals will be a scalar signal sigma, which allows to do detection, and a vector signal R, in fact a full residual, which allows to do detection indeed, but also isolation. Now, if we computing this quantity while the robot is in normal operation, then we will continuously do a check if this signal exceeds some threshold, a scalar threshold on the absolute value of sigma, so when it exceeds a sigma collision, and for the vector signal R, probably we take the norm so that if the norm exceeds some threshold, or indeed we could also work on components, but this is just for illustration. Then if this exceeds, then we have a yes answer, either of the two. If both of them are below threshold, then the collision monitor just says no, and we continue to monitor operation. But if a collision is being recognized, then we activate a reaction strategy. The reaction strategy may use, in particular, the residual R in order to change operation. So the first thing that the reaction strategy does at the control level is to deactivate the normal mode of operation, okay, and let the robot react to the detected collision, and possibly also to the isolated. And if we had isolation in place, then we could use in the reaction strategy also the signal R. The interesting thing is that if we use R or even sigma only, we may also recognize that the contact has gone, so that no matter how the robot reacted to this, there's no more collision in place, so that we can reactivate the normal mode of operation. Indeed, we may have lost track of what we were doing, or we may have been able to save something of the execution of the original task. No matter which is the case, we can reactivate the normal mode of operation, recovering from this colliding situation. Another comment are the external arrow that goes from reaction strategy to collision monitor. Because while we are reacting to a collision, a single collision we assume to have, but the robot may collide another time and another time again. But the nice thing is that we can continue to monitor collision and recognize new collision that occurs after the first one. So we have a permanent monitoring of collision in place. It's not a one-shot event. We can follow this over and over. And this is very important I guess. And we'll see also in some video what does this imply. So let's now generate this residual signal. Let's start with a scalar residual. And in fact, the scalar residual is based on monitoring the total energy of the system. So we compute a signal which is the difference between the actual energy at time t and some integral of the accumulated product between computable signals. So the velocity of the robot and the applied torque by the motor. So this coming from whatever open loop or closed loop command. And you see that the sigma is also inside the expression of the residual. And then we have to subtract some initial value of the total energy. If we start from 0, E0 will be 0, and so we can forget about that. We have to initialize the residual, we initialize it at time 0, and this difference between the energy and this integral, in essence, apart from the initialization of E0, is being amplified by a positive gain Kd. Now, this is, in fact, a computable signal. So we don't use tau k that we don't have, we are using only model terms and, of course, the same signal that we are generating sigma. In fact, you may compute this by evaluating the model terms, but you also can use the Newton-Euler algorithm for computing, for instance, the kinetic energy. By suitable calls, you can compute the generalized momentum and then do the product by q dot, and so you compute at least the kinetic energy. Then you have to compute the potential energy to get the total energy E, but in fact computation of the potential energy is simpler even for a large number of degrees of freedom. So this is the definition and what you can implement in your software. Now we can look at the dynamics of the signal. We need this for analysis. So we need to know what happens to this signal if a collision occurs or not. And it is easy to show that the dynamics of this, so the evolution of the sigma dot, as this form, so minus kd sigma plus kd, the product of the velocity of the robot times the joint torque resulting by a collision. So if there is no collision, tau k is 0, so the dynamics will be simply sigma dot equal minus kd sigma, and if sigma starts from 0, it will remain in 0. So this is very simple. But if a collision will occur while the robot is moving, at least some joint is in motion, then the signal sigma will be excited by the collision. So we can detect that the collision occurs. Of course, it's a scalar, so having information on which link has collided is impossible with just this scalar signal. Now, the presence of sigma in the integral, and of course for analysis in this evolution, gives to this residual generator the form of a stable first order linear field. So it's the terms in green is exciting the collision. If the collision is gone, so if the contact is gone, so tau k has gone to 0, then sigma, which is now at a certain value, will return automatically exponentially to 0 with the time constant 1 over kd. So this allows the system to be ready for a new detection. Okay, so this is also important. If you want to implement this method, it is good to have an idea of what are the signals that you're using. So this is, for instance, in a simulation in Simulink, you have the following situation. So on top, on the blue part, you have the dynamics of the robot, which is evolving, the real robot or the simulated robot, if you're doing some test on a simulation, in a simulation environment. The tau k is inside the robot. Of course, it's not a signal that you can hand over to the residual generator. But in fact, you're using Q dot and tau, and you're using Q dot and Q both for computing the scalar product of the input torque and times the velocity, and for computing the total energy. You just need Q and Q dot. You take the sigma output of this generator, you compare it with Q dot transpose tau, and you're generating a difference, and then you integrate this, and you compare, you subtract this from the current value of the energy, total energy, multiplied by the scalar gain Kd, and generate sigma again. And the correct initialization of the estimator, of the monitoring signal that's monitoring the total energy, should be exactly the value of the energy at time 0. So if the robot starts at rest, you initialize this to 0. And in fact, you have solved your problem. So this is the implementation of the formula that we have seen before. Okay, so you can see that you can recognize here a form of observer, an observer or a monitor of the total energy of the system, and this is being used to detect the presence of a collision. Now, what can we say? It's a very simple scheme. In fact, we are generating the scalar signal. It's model-based, so we need to have a good model in order to compute the total energy of the system. But because of the presence of the product of the tau k times the joint velocity, this shows that we can only detect colliding force torques, so wrenches that will produce work on twist at the contact. And this is shown by the following computation. Moreover, the scheme does not succeed in detection when the robot stands still. Why? Because Q dot is equal to 0. So Q dot times tau k will be 0, at least in the first instant. Unless the robot starts to move, the residual will not be moved from 0. The fact that Q dot transpose tau k is associated to the work produced by the wrenches on the twists at the contact, so I'm using this terminology now, which is more compact than always saying a generalized force, which is a force and a torque, or a generalized velocity, which is a linear and angular component. So wrenches and twists are more compact terminologies. So you can see that tau k is in fact equal to J transpose of k Fk, but then you recognize that J transpose and Q dot transpose J transpose of k is in fact the transpose of the velocity at the generalized of the twist, in fact, at the contact, so that this is 0 if and only if Q dot transpose tau k is 0, which means that either Q dot is 0 and Vk is 0, or that you have a velocity but the applied collision is in a direction which is orthogonal in a generalized sense, the same sense that we have seen in hybrid control, to the motion of the robot. So this detector fails when the robot stands still or when it's moving, but the colliding force at the Cartesian level is in a direction which is orthogonal to the motion of the link that is undergoing the single collision. Okay? So there is some limitation. In general, this may work. It's a simple scheme, but it's not a complete one. And here I have an old simulation, just the result to have an idea what does sigma do. Here we simulated a 7-hour robot moving its end effector on a Cartesian path. Close to the path there was an obstacle, so that the body of the robot, while moving, may collide, in fact, after half a second, while tracing the Cartesian path with some speed. Of course, this robot is redundant, so depending on may collide or not, but at some point it collides, and the sigma signal moves out from 0, and the contact is detected. Of course, we have to place some threshold. Here we put threshold at the value about 3 in absolute value. This could be interpreted as an energy, so this could be joule, whatever. So when this exceeds the threshold, then the contact is detected. And after a while, the signal, the contact is gone, and the signal returns to 0. So we can establish that the contact has gone when the signal is actually 0, or when it becomes, for a while, with a digital, let's say, filtering. We have seen this before for the recovery from actuator faults, when the faults were intermittent. So when it stays for a while, for a number of samples below the threshold, then we recognize that the collision in this case has gone. And here instead it's an experiment that we conducted quite after having introduced the whole methodology, I must say, because we focused more on the second type of residual signal, the vector one. But this experiment shows on a 6R robot what happens. So the robot is either at rest or moving along a straight horizontal line under Cartesian impedance control. This is not really relevant which controller was applied, just to handle possible forces occurring. Moreover, we equipped the end effector of the robot with a force sensor at the wrist, so that we can analyze what's going on. So you can see here different plots and different phases of this experiment. So the first plot is position, the second is velocity in just this linear direction, horizontal direction. Then the force measurement by the force sensor. This is just used for analysis. Of course, we don't want to equip the robot with an additional force sensor for detecting collision. By the way, we could only detect collision at the end effector level, not along the structure. Then we have the sigma, and in fact you see that this is expressed in watt, in the form of integral of energy. And then also the scalar product between the external force applied and the actual velocity of the end effector robot in that direction. Okay, so this is the setup. And now let's look at the various 6 phases. So we are focusing on what does the sigma signal. And in fact, you can see that it's 0 most of the time, only in some phases, in particular in phase A and in phase D and in phase F, although to a minor extent, is becoming different from 0, like we have seen before in the simulation in the plot of the simulation that I just showed. So in phase A, what happens? The robot is moving and the contact force is applied against the motion direction. So we have full detection. The force sensor measures component mainly in the x direction, but also a bit also in the y and z direction. And there is some work being produced by the external forces on the motion. In fact, it's stopping, trying to reduce the velocity, and you see that the speed, so we are still moving in the direction, but you see that perturbation on the speed between the desired one and the actual one. And also in the y direction is being traced, but almost nothing happens in the y direction. So this is a classical detection where the sigma signal works. Then in phase B, no force is applied, the robot is at rest, nothing moves. In fact, you see that x is not moving, it's staying constant, x dot is equal to 0, the desired and the actual one. There is a residual measurement of force because of the sensory hysteresis. Sigma is at 0, and there is no work produced by the external force, which is in fact not applied, and the robot is at rest. Then in phase C, now force increases gradually, but the robot is still at rest. It's being held by an impedance control that keeps the robot at rest despite the presence of some small force. So you see that sigma, although the force is present and is being measured by the force torque sensor so that we know that a force is being applied, but because of the no motion due to the Cartesian controller, the sigma signal stays at 0. In phase D, the robot starts moving again, and you can see this from the second plot. We have an x dot, you have a desired velocity, but in the direction of, in particular in the direction of the applied force, you see that there's a difference between the desired one and the actual one. This happens to be true also in the y direction. Again, because we are moving in the x direction, so for sure, and in that direction we are also applying an external force, so the sigma again goes out of 0. So this is the same situation as before, and the external forces are doing, the last plot, are doing some work on the motion. There's another situation where at this stage the robot stands still and the force is applied in a different direction, in fact in the z direction. So there's no detection. No detection because the robot stands still again, so return to 0. Now the last phase is the very interesting one, I would say, because the robot moves in the x direction, but the force is being applied in a direction which is orthogonal to the motion direction. So there's some coupling because of the inaccuracy of the application of force and so on. So you see that the signal is slightly excited, the sigma signal. So you have detection, but in fact you have a poor detection because of this orthogonality, because the fact the robot is in motion, because if q dot were 0 and x dot similarly, you would not see anything, as we have seen in previous phases, for instance in phase C. But indeed, the orthogonality, while the robot is motion, is the price to pay for having such a simple detection monitoring signal, just detection. So we move now to the vector version, so to the residual vector version, and more similar to the actuating faults, to the signal that we have generated for actuator fault detection and isolation. So this is the momentum-based isolation of collision. So we compare the generalized momentum with the integral of this signal, which includes q and q dot, which includes the applied torque to the robot, and we subtract also the generalized momentum at time 0 if this was different from 0. So if we start from rest, all this is gone. The residual is initialized to 0 as well, and we have a diagonal ki. You can recognize that in the integral we have the transpose of the skew symmetric, of the factorization matrix that satisfies the m dot minus 2s skew symmetric property again. So if we want to compute this, this vector is computable with all information that we have on the model, on the measurement on the robot, and on the applied torque. But so if we do a Lagrange modeling and we have all this term, we can compute this term immediately, but of course this may be very long. So if we decide to use a Newton-Euler algorithm, then you should be aware that the S transpose matrix, so the isolation of the S matrix per se, which is not part of the Coriolis and centrifugal term, that would be S times Q dot, and then S times Q dot is computable by a suitable call of the standard Newton-Euler algorithm. So we need the modified one, the one which has 4 arguments and where we can distinguish between the inner velocity and the outer velocity in the factorization. And in fact, we need to call n times in order to build the columns of the S matrix, and then we have the full S matrix, and we can do the transpose numerically and then multiply by the numerical value of Q dot. For the gravity term, we can still use the Newton algorithm as such. So we have a trade-off between computing this by recursive method numerically or evaluating the symbolic expression of our model, where we have the S matrix as such, and therefore also the transpose of it. Okay, so this is about computation. So this residual can be computed even efficiently. More details in the 2017 transaction on robotics paper that I mentioned at the beginning. Again, for analysis, what is the behavior of this vector R? And not surprisingly, we find again a decoupled dynamics, because Ki has been chosen diagonal, sensitive directly to the joint torque tau k resulting from a collision. So this looks like exactly like an actuator torque fault, but in fact this extra torque is not missing in the actuation. Indeed, if we had also such a fault, we would be in trouble. We could not distinguish an actuator fault from a collision torque, at least if we assume a rigid model. Otherwise, we could do this, and we will see it later on as a comment. So this is now sensitive even when the robot is standing still. As long as our joint torque is, our wrench, collision wrench, anywhere in the structure is producing some tau k, because of course it should produce motion, like the joint torque will produce motion. If we are hitting at the base of the robot where no motion will result from this collision, of course this method can be not, will generate nothing, and we should then resort to sensory information, either tactile sensing or a camera that observes that this collision has occurred. But then it's a different story. So on board, we have still this limitation, but generically, this collision will be detected as soon as tau k is different from 0. So this is our signal. There's no modulating velocity in this format. And in fact, and the dynamics is fully linear, by the way, so we can also write the Laplace transform exactly like we did for faults in the joint actuation, because at this stage we have reconducted the problem. So we have n decoupled first order linear filters with unitary gain and excited by a generic collision, which does not occur at the joint, it occurs somewhere, but as soon as at least one of the joint is being affected, then the residual will be, the associated residual will increase. And of course, multiple residual will be activated for collision that occur downward in the serial kinematic chain constituting the robot manipulator. Because of the structure of a filter, as soon as tau k is going back to 0, because we are in a post-interface phase, also the residual will go to 0, so we can recognize that collision is gone. And we can also use R for the reactive phase as long as R is present. Okay, similarly to the previous case, this is the block diagram of the residual generator. Again, initialization of the block of integrals as many as the number of joints. So the p hat of 0 should be equal to the p of 0, so 0 if the robot starts at rest, and otherwise the computation is very similar. So once you have seen the first of this scheme, I'm sure that you understand all of them, and therefore you are able also to reconstruct properly the formula in your system and also in a simulation environment, Simulink or Python or whatever. So there's no longer need to comment. Again, Ki is positive and diagonal. Now, some analysis of this. Indeed, if there are no noisy signal, no uncertainty in the model, and you can pump up the gain ki, let's say going to infinity or to a very large value, then the residual will reproduce whatever story of tau k. Indeed, if tau k remains constant, pay attention, tau k not fk, so the joint torque resulting from the collision will become a constant, then R will converge to tau k because the filter has unitary gain after some transient, which is short, even if ki is not that large. Of course, the larger it is, the faster R will converge to tau k. Otherwise, it will track, so be after tau k, closer enough to substitute in our analysis R by tau k or vice versa. So we take R as a proxy of the joint torque resulting from collision. Now, what about the isolation? This is very important. So, because we know that tau k has the structure of jk transpose, even if we don't know jk transpose, and we don't know fk that generated this, but if this is the case, so because R is similar to tau k, and tau k has always this structure, then if, from static consideration, if the residual will have non-zero component up to a certain index, let's say the index I, then, and then afterward all zeros, then we know that the collision has generically, so modulo some singular situation, occurred in an area which is up to the ith link. So this is the type of isolation that we are able to achieve. Okay, so we can exclude that the collision occurred, and this is for sure, occurred at link I plus 1, I plus 2, and so on up to n, if those components of the residual vector are 0. On the other hand, all the lower components have been activated, and in fact, we can understand that we could react to the collision by moving mainly those joints that have been affected, let's say, by the joint torque coming from the collision. So this is a kind of an involved reasoning, but if you reason about, we will see that we have an immediate consequence of the use of R as a reaction strategy. At the moment, we just can say that beside detection, we have also some isolation properties. So this directional information is very important. I commented this before putting this on this slide, but exactly what I just said. So this directional information can be used in the reaction, let's say, in the post-impact phase. So the few milliseconds after the contact. So this is in fact the reaction. So once we have recognized a collision with sigma or R or with both, and we have a yes, now we will use this information within the reaction strategy. So we have deactivated the normal mode of operation, and we are sending to the robot a tau R, which is different from the original tau. As soon as the monitor says that collision is over, of course we can reactivate the normal mode of operation. And the collision monitor in this modified block diagram from the original one received information on the internal robot state and on the control command. So, what type of reaction strategy you can imagine? First of all, in order not to bias the reaction to this collision from gravity, we will always use a zero gravity operative mode. So we will cancel gravity every time. Probably we were canceling gravity also before while moving the robot under the action of some feedback controller, regulator, or trajectory tracking. But certainly when we decide to react, the tau will contain always a cancellation of gravity, plus a tau prime, which may be different. So as soon as we detect a collision, and in fact we are now working with the isolator signal R, so R is over some threshold in norm or in component wise, then we activate this reaction strategy as said. So we could do several things. So the strategy 0 that we use as baseline to comparison is that we don't react at all. So the robot tries to continue its originally planned task and motion, which could be a disaster. But indeed, this is the 0 strategy. The strategy 1 is just stop the robot. So, in a sense, although we could even isolate the link at which the collision occurred, but just only detect, so no matter if we are using sigma or R or both, then we stop the robot motion. How do we stop as quickly as possible robot motion? Well, we could, if the robot is equipped with brakes, we could brake the system. However, if you break the system typically in an industrial setting, this is an alarm situation. So you cannot recover from this situation. You have to restart the system from scratch. So this is something that you would like to avoid. So the other way of braking without using the brake, which is an alarm, is to stop the generation of reference motion. So you keep the same, the last value of the desired position of the joint that you were executing while doing the trajectory. So you take the, let's say, the before last value, and then you switch to a high gain position control, keeping that value forever. So the robot will stop, but still operate under position control. So you may command the robot to restart if you realize that things have gone. So this is a very basic different operative condition. Braking will induce an alarm and a stop, a definite stop of the robot. You have to restart from scratch, unless the robot has a safety mode that allows using the brakes even without releasing control on the system, in a sense. Okay, but the most common situation, you switch to high gain position control, keeping the last position, let's say, frozen. Okay, so the last reference position generated. Okay, so these are no reaction and a very trivial stop reaction. What about the most interesting one? What I call a reflex strategy. So now you have to use the full residual, the R signal. So apart from compensating gravity, the tau prime is proportional with the diagonal to the residual itself. Okay, so this is, again, I'm using in the reaction the residual that has been used or is being used to detect and isolate collision. Why do I call this reflex strategy? Because in fact, apart from, let's say, letting the robot float in a zero gravity situation, we are commanding a joint torque which is like R in the same direction of tau k, so on the same direction of the torque resulting from collision. It's like if we are exaggerating the effect of a contact force in the Cartesian space, whatever point of the structure, at the joint level. So we are really amplifying the effect of this. So this is a reflex strategy because, in fact, if you hit something and you have a force against your arm, then you retract the arm exactly in the same direction of the force that you have experienced at the Cartesian level. Of course, you do this at the Cartesian level. In fact, you're doing this at the joint level because it's there where your actuation occurs and where your muscle operates. So you're moving the joints, but in fact, the effect is moving away at the Cartesian level, from the contact area. Okay? Now, this reflex strategy, I cannot show at this moment in this lecture any result for a fully rigid robot, although we have done this on the universal robot, which can be considered as a robot with rigid transmission. But we will see that this reflex strategy then takes on, so we are using the residual, takes on various modality if we move to a system which has joint elasticity, like the DLR lightweight arm and the KUKA as well, the KUKA lightweight arm as well. So there are, at that stage, then there are slight variation of this reflex strategy, but the principle is always the same. In fact, if you go back to the rigid case and you're looking at, you substitute to tau, tau prime plus JQ, where tau prime is KR times tau K, and in fact it's KR times the residual, but you make the substitution, the proxy, that the residual is the tau K, then the reaction of the robot is exactly the following. So the model in the closed loop in the reaction phase can be reorganized in this. So gravity is gone out of the picture. You may have Coriolis centrifugal term still there. You have the inertia matrix, but then on the right hand side is the collision torque that is moving the arm, and the KR is acting as its inverse, as reducing the effective robot inertia. So in fact, the KR, the fact that you're moving in the same, along the same torque, you're giving the same torque along the one that is resulting from the collision, is like reducing the effective robot inertia. So the same amount of collision torque will push away, accelerate more the robot, because the robot looks lighter, because this identity plus KR with KR large will divide component by component the inertia and all the other terms, so that the acceleration can be, as a result, much larger. So it's like saying you have a cow, this is your original robot, this is being hit by an external force, so you let the cow react like a frog that jumps away. So this is a pictorial view, of course, completely qualitative, completely rule of thumb, but just to understand why we are using the residual as a reacting strategy. Okay, so I would like to move on to showing you actual results, because otherwise you don't believe that this works fine. So at that time we implemented this method, and it was around 2006, 2008, on the lightweight robot of DLR, the lightweight robot 3. You can see it on the right hand side, it's a blue color, but you can recognize that this is exactly the KUKA lightweight 4, which is the, let's say, the outsourcing of the results that we developed for research together with the colleagues at DLR. So the first results dates back many years ago, and nowadays have become an industrial product, because in fact KUKA acquired the rights to use our algorithm and is using it probably with some modification, but no, it's not really relevant in their industrial robot of the lightweight type. So that robot had harmonic drives and therefore elastic joints, but was also equipped with joint torque sensor. So there's an extra sensor, in fact, but it's an onboard sensor which is used for general control. So it's the same sensor suite that the robot has, also not for detecting and reacting to collision, just for doing motion. The dynamic model of the robot with elastic joint, we have seen this as an example of a variation. You can, under simplifying assumption, the so-called Spond assumption, we neglect some term in the angular energy of the rotor of the motors, supposing that the reduction ratio is large, is a good approximation. In fact, the model looks like the rigid model for the first set of equations. These are the so-called link equation. On the right-hand side, however, you don't have the actuating torque tau, but you have the joint elastic torque, which are in fact written below, are the stiffness of the joints times the difference between the motor position and the link position. K is a diagonal matrix of high value, I would say, for harmonic drive. For variable stiffness actuation, you have the similar model, but K can be modulated and can be also very much reduced with respect to the case of harmonic drives. So, on the first equation, you have, however, also the joint torque due to the link collision, like in the rigid case. In the rigid case, you had the first equation with the tau, and you add the tau k. Instead, the motor torque commands now act on the motor, so on the second set of equations, which are linear, which are in fact the motor dynamics with the inertia of the motors times the acceleration of the motors, and then the elastic torques, which happens to be on different side or on the same side with opposite sign, because joint elasticity for the principle of action and reaction act on the motor and on the link in opposite direction. And the elastic torques, which are being measured directly by the joint torque sensor in this robot, are simply K times theta minus Q, so they appear on both sides. Now, you can see that we have a slightly different situation here, but the implementation of the residual method, in particular of the residual, both the scalar one and the vector one, but I will show you only the momentum-based method, can be done by the measurement. Now, there's another very important observation here. We mentioned that friction should be negligible, or if not, in the rigid case, you should model and include it and use it everywhere, like the gravity term and the other term that you use in the residual. However, if you're moving to a joint elastic case, because of the particular construction of the DLR lightweight robot and also of the following generation of KUKA lightweight arms, the friction at the link side is in fact negligible. The heavy friction is on the motor side. This is an important observation, because if you don't use the motor part in your computation, then the upper part is actually all that it is, because friction is negligible there. Okay? In addition, what are the measurements that you have? In fact, there is some redundancy there was some redundancy in the LDR system, because we had a motor position measurement by encoders, we had a link side position measurement as well, and we had also a joint elastic torque measurement. In our experiment, we used only the motor position and the elastic joint torque. Wherever we need Q, we use the expression of the elastic joint torque as a function of the stiffness of the joint and of the motor and the link position. So Q are solved from the linear equation of the elastic torque simply by saying theta minus k to the minus 1 tau j. So we are using, in fact, theta and tau j as such, as you will see, and theta and tau j to get a measurement of Q. There is also, in fact, in the robot, this is an exploded joint of the generic joint of the ALVR3 robot. You can see that there are many components, everything is on board, very specially designed, lightweight, and even for the motor components. But here you see the three sensor that we will use, the joint torque sensor with its digital interface, the position sensor on the motor side, but also there is a Hall effect link position sensor that has not been used because it's less reliable. It's used as a backup but is less reliable than the position sensor on the motor side and on the joint torque sensor. Moreover, the harmonic drive is in between and is the source of joint elasticity, for which the model that we have seen is more important. Now, how do you do collision isolation? Directed isolation, the most difficult problem for this type of elastic joint robot. There are a few alternatives that you can explore. The easiest one, and the one that we implemented first, the simplest one, is to take advantage of the joint torque sensor and in fact take the same expression of the residual for the rigid case, namely using the link dynamics equation only, the one where friction is not present because it's really negligible at that side of the elasticity. So replace the tau, the commanded torque, with the measurement from the elastic torques. So the expression of the residual, which now I label as REJ, just to remember that EJ stands for elastic joint case, but in fact the expression is exactly the same as in the rigid case. The only difference is the red symbol, where we are using the measurement of the elastic torque rather than the commanded torque like in the rigid case. And the dynamics of this new residual is exactly the dynamics that we expect. So I don't need to comment this any longer. Indeed, if you didn't have a joint torque sensor, but still joint elasticity, which is the case of the so-called serial elastic actuation or variable elastic joint, many times you don't have the joint torque sensor there, then you have two alternatives. One alternative is to use position measurement at both sides of the elasticity, so of theta and of q, and then you need to know the joint stiffness k, through which you reconstruct the signal tau j, which is the elastic torque that you don't measure directly, but you can recompute through that, and then you can proceed as before. This is the common use. There's also another alternative. You can modify the residual by adding not only the momentum of the link, which is the p as m of q times q dot, but also the motor momentum in the expression, which is bm times theta dot. And then using the commanded torque in place of the tau j. You can show that the dynamics is exactly the same as before. The only problem is that in this case, since you're using both equations, because you're using also the motor momentum, and therefore in the analysis and in the expression, you need to use also the motor equation, not only the link equation. The motor equation will be affected by motor friction. So you need to estimate value or compensate completely with a different method, which can be done, as we have seen in the previous lecture on actuator faults. The same method on the motor side can be used to compensate friction. But anyway, you have to deal with friction. Modeling and including it, or compensating it with another residual which is designed on the link side, on the motor side of the problem. So there are these two alternatives, but so you can implement in particular, the first one maybe is simpler, but you can implement it in place of this if you don't have a joint torque sensor. So this is not really a limitation. Indeed, in the presence of joint elasticity, also motion control as a whole is more difficult if you want to regulate to a position or to a desired position of the motor or of the link. If you want to track a link trajectory, you have more complexity. So even in our case, the reactive part can take different flavor, although all similar to the reflex strategy. So we will see that different strategies of reaction are possible, and in fact we have implemented all of them and also compared them on the lightweight robot 3 of DLR. So we start with a general control law which uses full state feedback, and in fact this is the controller that is being used by DLR for their motion control, and this uses motor position and velocity or some numerical derivative obtained from the motor encoders. the joint elastic torque, which is being measured, and also its derivative. This constitutes, in fact, a new set of states. Instead of motor and link position and velocity, you have motor position and velocity, joint elastic torque, and its derivative. This represents a full state for the system. And here you see that the generic torque controller for this robot uses the motor position error with a Kp, then damping out the motor velocity with a Kd, then an elastic joint torque error, the tau j desired minus the measure of joint torque multiplied by a different gain, and then damping also this derivative numerically obtained, plus an elastic joint torque feed-forward command for doing tracking. So I'm presenting this because, in fact, the various reactions are implemented by choosing proper value for these quantities, in particular for the Kp, for the tau jd, and that's it. Okay. Now, the zero gravity condition that we mentioned should compensate gravity. However, gravity is present on the link dynamic, while we have a command on the joint, on the motor side. So we cannot really cancel directly. So we cancel it in many different approximate ways. The one that was implemented at DLR was just using the motor position measurement. So it was reconstructing the JQ by measuring the motor position and computing a J bar term by a contraction mapping, an iterative scheme, very quickly. At every sampling time, you were feeding the theta that you measure from the motor into the balance equation, the static equation that you see on the right hand side, which on the link side, when nothing is moving, so in a quasi-static situation, this is the approximation, this boils down when q dot and q double dot are 0 to k of theta minus q equal j of q. So you're feeding the measure of theta and you're solving this numerical equation by contraction, starting from the previous q that you have. In fact, this is very efficient. So in 2-3 iteration, you get a new q which is associated to the theta. And you're using this q, which is not measured, but is obtained from the measurement of the motor position, in the expression of g. And so you're compensating in this quasi-static approximate way the gravity. So we have everything in place to introduce the reaction strategies for the elastic joint case. So remember, the strategy 0 is continue to do whatever you were doing. Strategy 1 is just stop the robot by breaking it or breaking the joint, or better, stopping the motion generation, the desired motion, to the previous value of configuration QD, and using high gain to stop the robot at that position. So strategy 0 and strategy 1. Strategy 2 is just floating. So putting the robot in a zero gravity condition. So the feed-forward torque that we are sending to the previous full state controller is just this approximate gravity compensation. And we don't give a reference position. So we put Kp equal to 0 so that we could go everywhere. We just float without gravity under the action of the collision. The strategy 3 now is the closest one to what we called reflex strategy in the rigid case. In fact, we call it reflex torque reaction here. Again, Kp is set equal to 0. You compensate gravity, but you add in the desired joint torque also a term which is proportional to the momentum residual, the Rej in this case. So this is very close to that. Gravity compensation plus proportional to the residual reaction. So it's the closest to the rigid case. We have also another modality which is called admittance mode reaction. So you still compensate in the tau j desired the gravity, you keep the Kp, so you keep a proportional, a motion controller, but you assign as reference velocity the reaction to the residual with a different Kr. It's called Kr theta, which means that as soon as the residual goes to zero because collision is no longer there, the robot will stop because the theta desired velocity will be zero. Okay, so these are the option together with strategy 0, no reaction, and strategy 1, just stop. Of course, you can have further possible reaction in these cases, combining strategy or using impedance control. Research has proceeded along this direction using the concept of momentum-based residual for isolating collision. Two interesting things that we have done is time scaling. So trying to preserve some reaction, some part of the task. So you don't give up the path at the Cartesian level, typically, but also at the joint level. You just stop the time or reverse the time. So you move back on the same path that you were tracing when you get a collision. And if you have somebody pushing you back, you retract. And as soon as the contact has gone, you recover the same path. So you're giving up only the time. Or you try, and in the presence of redundancy, you could do this. You have a collision somewhere, the end effector is doing a task. You try to preserve the task of the end effector while accommodating the reacting torque in the null space of some dynamic behavior. And this is a very important and very interesting situation that we will see through some video. So, we made the first experiment using a dummy head, so something that mimics, let's say, the skull of the human, with some accelerometer mounted on it, because the accelerometer is the first thing that we notice the contact. So we are not using this for reacting, just for comparing strategy. And the robot is moving first horizontally, moving the first joint at 30 degrees per second, and therefore the end effector with a linear velocity which is proportional to the stretch of the arm, which is about 1.5 meter along the horizontal direction. So we use this for setup. And here you see some video. First, strategy 0. You see that this video were run at DLR. You see the dummy head on the right. So the reaction, no reaction, is just moving the robot. The robot and the effector should go in a position which is slightly beyond the dummy head, and no reaction occurs, so that quite slowly we hit the head of the emulated human, and of course we damage it. Now, strategy 2 is the first reactive one, with rather low velocity, so the robot will go in a float reaction, but in fact it will just stop because there will be no contact any longer. So let's see what happens. We touch, but we immediately stop, and the robot now is floating. So if you move it around, it will just follow you as a reaction to a new force. You see that the monitoring of collision is still going on. So we first hit the dummy head, and then we react and we stop. But since we are in the floating mode, we continue monitor if there are new collision. In fact, if you keep it by the hand and move it around, it will just follow you in a passive way. It's just like the joystick without a force torque sensor, not there as a behavior. Now, how long will it take to detect collision? So because we had the accelerometer mounted on the dummy head, we could also make a measurement, an accurate measurement of what happens, sample by sample, with a sampling time of 1 millisecond, to the various signals. So here you see a colored trace. The detection on-off, let's say the 0-1 index for detection is the magenta one on top. And the first thing, then the red one is the measured joint torque, and surprisingly for us at that moment, this signal is not really sensitive in the first few instants. The residual is the blue one, which is oscillating because of noise, so there should be a threshold. And the green one is the dummy head acceleration, which is 0, because we don't touch the head while moving. And it's the signal that, the first one that goes out of 0 when you have a hit. So when you see at the millisecond 0.496 seconds, so 496 milliseconds after the start of the experiment, we can say that there is a collision. And the accelerometer, of course, measures something. The residual stays still for a couple of samples at 0 and then start increasing. Okay, so there is a delay in computation, but the delay is of the order of milliseconds, so of 2-4 sampling time, which is quite good. Okay, indeed, if you had increased the KI, the gain of the residual, you may have seen this one step ahead, but then you would have increased also the noise in the normal condition. So this is just a qualitative idea, or even a quantitative idea, of how fast you achieve reaction. Because you wanted now to compare the strategy in a quite repetitive way so that the environment is always the same, we decided to also make some balloon impact experiment. So we fixed the balloon, we inflated several balloons, having the idea that the balloon, while tuning the gains, may explode, so we need a replacement, but in fact this never happened. Okay, so at this stage the balloon is also compliant, so we could also expect some increase some velocity, the speed, so that the contact could occur with higher energy, but still we have a compliant environment in this case. So this was, again, a preliminary experiment where we could compare things. And you see here some snapshot of one video. The robot falls down on the balloon, hit the balloon, press on the balloon, then react and goes away. Okay, and the various reaction using the various strategy. First, let's see a balloon impact with the strategy 4, the admittance mode reaction that we have not seen before. So far we have seen strategy 0, 2, and now strategy 4. So we have a faster motion at 90 degrees per second in a coordinated motion, so we don't care about the individual point, and the hit will be close to the end effector. So you see that it hits, press a bit, force is being generated, the residual increases, the reaction is by admittance mode, the value of the residual is given to the desired velocity. Then as soon as the robot leaves contact, the residual goes to 0, the velocity goes to 0, the robot stops. Rather in a, let's say, impulsive way, okay? Rather a stiff stop in case of admittance mode. Now, we did several other experiments with the balloon impact, and now I just show the comparison of the profile of the residual at joint 4, remember that there are as many components at joint, and of the associated velocity of joint 4 with this balloon impact using different strategies. So on the left hand side you see the residual, which is proxy to a torque, a joint torque. On the right hand side you see a velocity profile. you see that the velocity profile for the joint was a kind of a trapezoidal one, and then the residual on the left-hand side, all residual for all strategy are 0, more or less sensitive to noise while moving. First, no motion, they are all 0, then you see that they are kept between a 3 to 4 Newton meter, which is the original threshold that we are using, and then all of a sudden all jump up while the velocity goes to 0, around 0.5 seconds. Now the strategy 0 is no stop, so continue to do, and the final positioning was inside, a bit inside the balloon. So if you don't react, you stop because the motion is completed, but you keep contact with the balloon. So this is in fact the torque, about 35 Newton meters, that is being felt at steady state at joint 4 because we are pushing on the balloon with the end effect. And on the other side, you see that the magenta profile, there will be some motion and then everything stops quite immediately. Okay? So there's no reaction and I'm keeping contact. Imagine that instead of the balloon, you were the one being hit with no reaction, and you're not so soft as a balloon. You will have a high force on your, let's say, body, and the robot stops and nothing happens. So this is not really a nice situation. The second strategy would just react and stop. So here you see strategy 1. So you react and stop, but still you're in contact with the balloon, and in fact you're pressing the balloon, and the equivalent force of pressure at the balloon at joint 4 is 10 Newton meters, so still quite large. With all other strategy, in fact, you bring back the residual to 0, which means that you detach from the balloon. So really you react, reflexing with different modality, the admittance mode, the reflex mode. In every case, you bring back the residual to 0 and you stop. And in fact, the fastest stop is obtained with the admittance mode. The other two are the yellow one, strategy 2, is the floating, so compensating gravity and letting the robot move accordingly. And the strategy 3 is the closest to the rigid case, is the reflex strategy. You see that the behavior of the residual on the left between the green and the yellow plots is pretty much similar. On the other side, instead, you see that the fastest reaction using the residual is the admittance, followed by the floating, and then followed by the reflex, which gives a more smooth behavior. And in fact, I like the most the strategy 3, as it will be seen in the following video. This is me some years ago, and on the left hand side, this is a first impact at 60 degrees per second, so quite fast motion. On the left hand side in admittance mode, on the right hand side, the strategy 3, the reflex torque mode. Remember that in both cases, if contact is released, so after the collision, the residual goes to 0 and the robot will stop anyway. But it's ready to monitor new collisions. So you will see in this video the first impact and then what happens in reaction to new forces applied now by me on purpose on the structure in admittance mode or in reflex torque mode. And you can tell pretty much the difference, especially in the following phase. So this is the hit, stop. I was pretty much impressed, and everybody in the lab was impressed. In fact, everybody wanted to try it later. And you see that I can push and the robot goes away and stops. Stops pretty soon, because as soon as the residual goes to 0, the desired velocity in the admittance mode controller, remember, admittance mode is giving a velocity proportional to the force. Here the force is not measured, but is reconstructed from the residual. There's no joint torque sensing at this stage, not even along the sorry, there's no explicit force sensing. There is the joint torque sensing, but in fact the same strategy could be applied to a rigid case. So this is just a way for going around. And the reflex torque strategy, instead, you will see a much smoother reactive behavior after the first impact and also the following contact. You see that the robot is slowly moves away. In fact, you get very much dependability here because you trust what you're doing. You can move around softly the robot in a very smooth way. In fact, this is the repetition of the same experiment but with a higher speed at the first impact. And please note that the way in which the robot reacts, so in the reflex mode, is different. So it's not going back along the same trajectory. It's just reacting, and we are amplifying the motion at the joint level with our reflex strategy, remember, letting the robot see even lighter than before. This is the effect of the reflex strategy. And depending on how you impact my arm, you will react. So not necessarily going back, you may slide along the arm and you may have different type of reaction, all natural, like the contact force that you are exerting. And this is what happened here. And then from there on, okay, you can tell that different contact and collision occurs. Okay, I think that this long lecture, we make a break now, so this first part stops here.